Hey there, welcome back, physics friends. So today we're going to continue and talk about how we solve rotational equilibrium problems. Take a look at this beautiful Calder mobile. You can see a bunch of his work at the National Gallery of Art in D.C. whenever it opens back up again, of course. So in these pandemic times, who can say when that is? Okay, so this is where we left off. What is actually being balanced here? So this is a meter stick that is not initially balanced at its center of mass, which would be presumably at the 50 centimeter mark. So here we've got some weights, and they're a certain distance away from the fulcrum. We could say the lever arm is from there over to there. These little marks on the weight holders help you out with that. So there's a weight over here, and there's a lever arm distance from there to there. This is perpendicular, so of course no angle to worry about, or if you prefer, the angle is 90 and the sine of 90 is 1. But what's going on the left? Well, you could say a couple of things. First of all, the tendency might be to say, well, isn't it the weight of the left side of the stick that's being balanced out with this, and of course the weight of the right side of the stick? And that is true, but that's way too complicated, for crying out loud. So why we use the center of mass idea is because it eliminates the need for that. We can assume that all of the mass is located at the 50 centimeter mark or wherever the center of mass happens to be. So if in fact that is true, then we can pretend that it's all true. We can literally pretend as though all of the weight is acting through its CM, which is indicated where that black dot is. So then we can just go back and treat it like a regular seesaw problem and say that the weight of the stick multiplied by the length from the CM to the fulcrum is equal to the weight that's hanging multiplied by the length from it to the fulcrum. And there's absolutely nothing wrong with this approach, and it sure is a heck of a lot easier than any other approach. So again, we can just literally pretend as though all the stick is located at its center of mass or center of gravity. Yeah, this is the beauty of the idea. We can actually treat it mathematically as though it's all there. In fact, that's even literally true if you think about it. You've probably held heavy things before, even like a pizza. You can hold it with one hand as long as you are balancing the center of mass. Okay, now, here is a good example problem. It's so-called scaffold problems. This is the problem where it doesn't have an obvious fulcrum. It looks like it actually might have two fulcrums. And in truth, it really has an infinite number of fulcrums, but we'll get to that in a moment. So we've got a painter who is on some kind of suspended scaffold. How do we find the tension in each cable? Well, let's throw some numbers in here in a moment, but let's talk about, first of all, what we need to remember is that translational equilibrium and rotational equilibrium are both important. We have to know the weights of the painter and the paint and the beam, the length of the beam, and the location of the painter and the paint and the center of the mass of the beam. And of course we have to know the locations of the cables, but for this problem I think we're just going to assume that they are on the extreme ends. Okay, so some numbers. T1 and T2. Presumably not equal. They would be equal if the painter and paint were in the direct middle on the center mass of the beam, but, why would we do that simple problem? So, T1 and T2. T1 is located at 0 feet. T2 is located at the end of this 10-foot long board. We're assuming the center mass of the board, which is 80 pounds in weight, is at the 5-foot mark, right in the center, and we're assuming that this 170-pound painter and paint is located at the 3-foot mark. So, let's take it from there. First, we got to do the translational equilibrium. That's the sum of the forces up equal the sum of the forces down. Well, let's go back here for a second. So, what's acting up? T1 and T2. Those forces on the beam are directed up. What's acting down? Well, that's just going to be the painter and paint, which is 170. So, T1 plus T2 equals the weight of the painter plus the weight of the beam. Ooh, I almost forgot that. So, T1 plus T2 equals 170 plus 80, and that's 250. Now, take a look at that. Oops, sorry, too fast. T1 plus T2 is equal to 250. That is one equation with two unknowns, and heck, there's an infinite number of solutions to that. So now we got to do the rotational equilibrium part, which is tricky. What's a clockwise moment, and what's a counterclockwise moment? So, all right, what I do is I choose a so-called pivot point. It's the point about which we can sum up the moments. We choose a point where the easiest way to do it is to choose a point where there's an unknown force applied. You'll see why that works out in a moment. So if I go back just a little bit, I'm going to choose the leftmost point here as the so-called pivot point. And I'm going to pretend that everything that's making the beam rotate clockwise about that fashion is a clockwise moment or clockwise torque, and anything that would make it rotate counterclockwise about that point is a counterclockwise torque. So, looking at this, if this is this leftmost point right here where it's 0 feet, if that is the point that I'm calling a pivot point, then the painter and paint are a clockwise moment or clockwise torque because they would tend to make the whole shebang rotate clockwise. The weight of the beam itself acting through its center of mass is also a clockwise torque or clockwise moment because it would tend to make it rotate about that point. On the other hand, there's got to be something counterclockwise, and that is T2, which would tend to make it rotate counterclockwise or anti-clockwise if you prefer. Okay, so I chose the leftmost part of the beam where T1 is located. So then we can say the mass, moment of the painter plus moment of the beam acting through its center mass is equal to the moment due to T2. So that's 170, that's the weight of the painter, times 3, plus 80, the weight of the beam, times 5, that's its distance, is equal to T2 times 10. And lo and behold, we can solve that bad boy for T2. We do that and we find out that T2 is 91 pounds. When we go back and plug it into our translational equilibrium problem, we get T1 equaling 159 pounds. So you see, that's actually not that big of a deal now, is it? Well, the rationale is I certainly could have also chosen the rightmost point as the pivot point. I could have chosen the center of mass of the beam as the pivot point. But any other point that I choose that doesn't have an unknown there makes it tougher to do. It ends up giving you an equation with 2 unknowns. And geez, you don't want to do that if at all possible. So sometimes you can't avoid it. But if you can avoid it, please do avoid it. Okay, so this is a more complicated problem called the ladder problem. We're going to get to this one in a moment. I actually want you to think about this scaffold problem one more time. So go back, and now I want you to imagine, how would you deal with this if T1 and T2, in fact, were not straight up and down, but rather were at angles? So T1 is kind of, shifted over here to the left, and there's an angle with respect to vertical, and T2 is shifted to the right, and there's an angle with respect to vertical. And if you're thinking, well, Sean, I bet we'd have to break it into components, you'd be absolutely right. You still could do it, but you would have to break them into components. And it does make it a little bit trickier, but it would just mean that the up component of T2 is what is acting up, and the up component of T1 is what's acting up. And then, of course, if you are smart and you still choose your leftmost point on the scaffold as the pivot point, then it's not a much more difficult problem, but it's a little more tedious. Okay, to the ladder problem. So here we have a ladder. Sometimes they throw in coefficients of friction here because physics professors can be just mean, but we're not going to bother with that. We've got, let's say, a 4-meter long ladder propped up against a wall at an angle of 60 degrees with respect to horizontal. Now you got some reaction forces against the ground, horizontal and vertical, and there's a reaction force from the wall. Let's assume that the ladder has something that's known as a ball joint or a cylinder joint, such that it just exacts a direct reaction force left onto the ladder. The ladder's weight is going to be 250 newtons acting through its center of mass, which is at the midpoint. And we're going to place a 1,000 Newton person standing on the ladder about 1/3 of the way up. Okay, so here is your problem. Excuse me. That rectangle on the right is, of course, the wall. So horizontal force from the ground and vertical forces from the ground, indicated as H and V. The 1,000 Newton person is 1/3 of the way up. That is indicated with a down arrow, and the 250 Newton weight of the ladder is acting at halfway point. And then F is exerted from the wall. It's a reaction force from the wall, and that's at the top of the ladder. Okay, how do we do this? Well, the translation part's pretty easy. 250 down plus 1,000 down equals only one force up, V. So the vertical force is equal to 1,250. We also know that horizontal has got to be equal to, H has got to be equal to F. So there you are, not such a big deal. But for rotation, it's a wee bit trickier because well, I'm going to choose the bottom leftmost point where it hits the ground, where the ladder hits the ground as the pivot point. That, of course, makes sense. I'm sure you would have done the same thing because it eliminates the need for h and v to be in the equation since their distance is 0 from the pivot point. But where does these angles come in? Well, let's take a look. So I said that the length of the ladder was 10 meters, and I now realize that I need to tweak this just a bit. Give me 1 second. Okie doke. So 1,000 is the 1,000 newtons is the weight of the person. They are a distance of 1/3 of the way up the ladder, which, since it's a 4-meter long ladder, they are 4/3 of the way up the ladder. Sure hope you can see that. But where's this cosine business come in? Well, if you notice, that happens to be 1,000 newtons directed down, but the actual distance, the horizontal distance, is in fact the adjacent side of that, which makes it the cosine component. So 4/3 times the cosine of 60 degrees is the actual, that's the way that we express the fact that that 1,000 newtons isn't a full 1/3 of the way up. It's actually 1/3 of the full distance times some angle. So that is, I know it's quite tricky, but another way to think about it is if the angle had been 90 degrees, that the cosine of 90 is 0, and that would mean that it is imparting no torque actually onto it at that point. So, and if the angle is 0, cosine of 0 is 1, so it's imparting a maximum torque. So 1,000 times 4/3, again, that is 1/3 of 4 up the ladder, times the cosine of 60, plus 250. Now, it's 2 meters away from the ground, but that's 2 meters up the ladder. It's 2 meters times its component to make it the horizontal version, the horizontal component of the weight, and that is 2 times the cosine of 60. That is going to equal the force from the wall multiplied by 4, but the sine of 60 because that's the vertical distance up from the ground. Boy, oh boy, I know it's definitely tricky. That's why I'm saying here, why cosine above? We need the perpendicular distance that the weight forces are from the pivot, which is to the right. And similarly, why sine above? We need the perpendicular force that the wall is from the pivot, which is straight up. So there you have it. Definitely, it does get a little bit tricky. Whoops, I went a little too far. Sorry about that. So, and of course, we actually take this approach in solving problems with trusses, but we don't do that here. If you end up studying engineering, then you get into the greater, gorier detail of all of that. In fact, you'd even be forced to take a course or two called statics. Okay, friends, I hope this has made some sense. Shoot me an email, seanplally@gmail.com. I do apologize. I go through this rather quickly because I don't like the videos to be longer than 15 minutes. I think it's just too long for you to digest it. So, but I do that at the expense of slowness. I go a little bit fast. Okay, see you soon. See you on the moon.